Hey, what's up folks? Welcome back to another Layer by Layer. In today's tutorial, we're going to take a look at a new project that we're working on. Let's jump into Fusion. So this is what we're working on. It is a fun animatronic wings. So it's a set of wings that uses servos. And here's a little video of our prototype in action with the wings mounted. So this uses the Adafruit Feather M4 as the microcontroller. And to power the two servos, we're using the Adafruit Servo FeatherWing. So that gives you 8 channels, so you can have 8 different servos doing things. And it's all running on CircuitPython. Very sweet. So I want to talk about the design of the servo horn attachments and a little bit of the mounting bit. So there's the demo, and let's kind of jump into what we have. So here's the CAD assembly. I have one wing set up here, and it was really important to get the joint set up so that I can simulate the movement of the servo horn. So this is a joint that's attached to the servo, and you can see here we have some degrees of freedom. So really it's able to come out here, and then it can go back up here. So it's about 90 degrees or 120 degrees of rotation. So it's not too much here. But what's interesting is the way the load is being counterbalanced. So underneath the servo is this ball bearing. It's a ZZ608 ball bearing, kind of your standard size. And what it does is it offloads all of the weight from the shaft of the servo down here. Because of the way it's mounted, we need to have this counterweight. So it works out pretty well. So I'm going to kind of step back into the timeline and kind of walk through sort of the design. So really the first thing was to kind of create the base plate to house everything. So this is going to be worn on your back, as you saw in the demo. And I just needed to make a couple measurements, really. The two main measurements, it needs to fit on your back, and it needs to fit on the bed of my 3D printer, because I just want it to be one piece. Or at least one piece for the backpack piece. And then we have these 4 slots that will act as attachment points for the backpack straps. So that's why I have them set up here. They're fixed numbers right now, but we could totally add user parameters. And really what makes this neat is that I can adjust the overall dimension of the width and the height of the base plate, and then these slots will actually stay retained to the edges because I've assigned them with some sketch dimensions. So I'll do a little demo here. Let's change that value there. And you'll see the 4 tabs stay positioned because I have these very simple, they're just sketch dimensions that says, hey, you should be a certain distance away from this. So that's why I have these set up. And let me undo that because it's not the shape we want. But yeah, it's very symmetrical. It's drawn like in the center. So if you jump into the sketch, you can see I just did I really just did 2 slots, and then I mirrored them. You can see all the different mirrors right here of all these little lines. So that's how that's working. It's a nice set of mirrors of shapes. And this could totally be changed up. We can add some more curves and things like that. I just wanted to have something that was easily adjustable and kind of has some shapes to go worn on the back. The next things I did was I had to model up the servo. So the servo is, let's take a look at it real quick. This little guy is a high torque, all metal servo, and it's pretty high power as well. So here it is. It's from Adafruit. It's the high powered, high torque, full metal gear, the MG92B. So unfortunately, the servo doesn't have like super great technical drawings, but I was able to go to their website. I think it's Tower Pro Tower Pro. You go to their website and they have a data sheet and you can pull some numbers from there. But I did have to use my calipers to kind of figure out the distance between these mounting holes. But I got those, so if folks want to use this servo, I have it uploaded to our GitHub repository, which I have linked in the description of this video if you guys want to grab that. But what's interesting about this servo is that I designed it so that the shaft of the servo has a rotational joint. So I can't show it right now because it's not grounded, but if I did ground it, or if I open this, you can see the thing moving. So I'm just going to go ahead and open, and you'll see how I set it up. I set it up as a 2-component piece, so I have the body that's grounded, and then I have a spline here, which is like independent. So if we look at the joint, I have it hidden because I don't like to see it when I import it. It would look like that. That's the joint there, and it is a revolve joint. So I can move this. You can see it moving around. There's no limits to it because it's just kind of rotation. So it's free to rotate 160 degrees. So to build that into the servo, I think it's really helpful because then I can simulate it a little bit better, I think, doing it this way. So that's cool. Not too much here in the timeline to create it, but it's got some shapes here. Cool. And I've already tested it. The mounting holes are correct, and the sizing and fitting is pretty one-to-one to what I have modeled, which is nice. So here it is. After bringing it in and modeling that up, I had to figure out how to secure the servo to this mounting plate. So what I would do like years ago is I would try to do everything in one piece. So I would integrate all the tabs into the backpack. But as years go on, I print, we could do that, and it's all integrated, and that's great. But it would take maybe 4 or 6 hours, and then you find out that you're off by 0.5 millimeter. So then that whole piece is not useful. So I figured let's make it all modular. So the servo attachment will be separate from the backpack base plate because we can quickly print out a small servo attachment as opposed to printing out the whole base plate. And that's something that took me a few years to do because I just have that mentality to make everything simple by having a single part as opposed to many parts. And because we're 3D printing and we're trying to get this really quick, we need to figure out the tolerances right away. It's better to have it modular. It just is, at least for this medium. So here I'm creating some sort of mount for the servo. You can see here that I have some offset there because as I was making this, I realized that I actually can't have this surface flush with the surface of the servo because of just the nature of using a ball bearing, which we'll get into. But I have these 2 slots on the sides, and those will be used to mount the servo holder to the base plate. Then I have these 2 thin walls here that extrude upwards. That way we can kind of attach it to the tabs, the mounting tabs of the servo. And if you look into the joint, it's just a rigid joint there, so it's just fixed in place. And the way I joined it was I think I picked one of these edges and just tied it to that edge. And then I added a little bit of an offset here, gap right there for some tolerances. So if you look at it from the top, you can see that I'm a little bit off there and a little bit off there just for clearances, right? Because the tolerances, you tend to expand a little bit, or maybe it shrinks a little bit. So I just want to have those there. And the next series of extrusions are next. Let's see what we did here. Just kind of fleshing out the holder here. So if we hide the servo, you can see I have this kind of hollow circle here. And instead of having all of this be one piece, you'll be printing a lot of stuff. And it's just a thin wall here to elevate that servo. So that was a kind of neat trick, is to just make a shelled wall as opposed to creating a whole, a whole solid to elevate it. And then I have these walls here on the sides that will kind of clip and hold the thing in place. So that's what's going on there. The next stuff I create is how am I going to counterbalance all of the load on the servo arm. I haven't created a servo arm yet, but in my head I figured let's use a ball bearing to offload the weight. So I have this extrusion here. So really it's printing so far. If you look at it in this orientation, the servo attachment, the servo mount can print without any supports. Nothing so far has overhangs. Everything just kind of extrudes up, no issues there. So as I start sketching out, I'm starting to create this geometry for press fitting a ball bearing in the center here. So as I make one more extrusion, you can see I kind of trim away that extra fat. We can say trim away some of that extra material, and that way we only have a ball bearing, a nice holder for the ball bearing. And still, you can see here, there aren't much overhang. You can totally print out, this geometry here without any support because it tends to kind of taper inward, which is really nice. And then I actually import the ball bearing and I affix it to here via a joint. So now you can see here, it is offset, right? It looks like offset. Originally, I had made this whole thing centered with the servo mount, But if you look at the servo itself, a servo is not symmetrical. It is offset. So if you look at the body of the servo and the shaft of the servo, they aren't actually lined up symmetrically. It's symmetrical like this way, but not this way. So that's why I had to be real careful with the positioning and the sketching of the ball bearing. So if you look at the sketch, you can see here, looking at it from the top, it is perfectly going down the center, and it's concentric with the servo shaft, the shaft of the servo. So that's how I created that. Just had to offset those series of concentric circles. And that's really all that it took to make that. And I have it a little bit out there. I created this cutout at the bottom so I can pop out the servo. If this wasn't here, it would be hard to pop out the servo because you don't have much here because it's press fitted. It's not getting secured with glue or anything. It just literally press fits. Tiny bit of tolerance in between those surfaces too. So that's how I got it. It's just a fixed joint. Okay, the next stuff is to create some of these mounting holes so that I can add a screw in there and a hex nut on the back here so that I can secure those two mounting tabs. And at first I didn't think it would print out good, but it prints out fine. I ended up just making the hole slightly smaller, so it's a 2.5 millimeter diameter, and then using an actual screw tap, a tapping tool, I can create those threads so that it has nicer threads. Because straight out of the printer, of course you can model your threads here, but it's such a small diameter that I don't think that would resolve well unless you were printing with like a DLP printer or something with more high resolution. But all this is designed for FDM printing, and this is kind of the smallest, I think, geometry you can make before things get a little messy. But it ends up working pretty well, and it's not too thin. It's just the right amount of sort of thickness to print and be reliable and sturdy. All right, the next series of stuff is kind of smoothing out some things with some fillets. Not much going on there. Let's move forward. I think at this point we're creating the servo arm. So the servo arm is what gets actually attached to the shaft of the servo so that we can get some motion. So looking at its profile, it's pretty simple. It's just a series of lines, and there's a fixed value for the length, and I try to keep a consistent thickness of the profile, so it's got a 4 millimeter thickness going on here, and it's centered here. So instead of like sketching it out in place where it already is, I decided to sketch it in the center of its own component, of its own origin, so that if we ever need to use some mirroring features, we'll have a very symmetrical design because it was drawn in the center of its origin. So once I kind of flesh out that main thing, the main shape here, the extrusion, just a couple extrusions here, I had to create some holes here as well. Then I apply a joint, so I attach the servo arm to the shaft of the servo. And what's interesting, if you look at the joint, you're probably thinking, oh, that's a revolve, right? No, it's rigid because the revolve has already been assigned to the servo, which I think is great. That's a great way to do it. Because when you import, if you import a design that has joints, those joints are movable and editable inside your assembly. So that's really nice. I wasn't too sure if that would work, and it does. So now that it's attached, I can actually start moving this. And you can see here, well, that's not moving because it's not grounded yet. Sure, the servo is grounded, but the servo is attached to this piece, and this isn't attached to anything. So that makes a lot of sense if you think about it. So what did I do is, well, this little pin here grounds the servo holder. So now with it grounded, I can manipulate and move and test the degrees of freedom on this. And you can see here, I had to be very careful not to crash into it. Because if you look at the servo's orientation, if you try to go this way, you're going to crash into it. But because they're wings, your wings can't do that. They would intersect with each other. So that's why it's positioned this way. So if we start to rotate it this way, about 120 degrees going down, you can see here that I can kind of complete the whole area here until I crash into it. But even the wings, if they're coming out, they don't need to spread that far. So I have a little bit extra clearance there, which is great. And you can see the wiring just about clears this area. So I actually have the wiring come up and then out this way and then down here. So that was strategic placement there. So once I figured that out, then I had to figure out how do I attach the bottom of the servo arm to the center of our ball bearing, because that's really what we need to do. The ball bearing is press fitted and basically rigid jointed to the servo horn itself. So that allows this center area of the ball bearing to be free to spin and rotate. So what I needed to figure out is how do I get this hole from the servo arm to be fixed to the center of this guy. So originally I was thinking, oh, I could just extrude out a tube, a cylinder, so that it would be press fitted through the center of our ball bearing. The problem with that though is the way it's already designed is I would have to probably use some support material or get rid of these fillets and have it printed on this way. But I really wanted this surface here of the servo arm to be flush with the bed of the printer. That way I have a really nice surface to adhere other pieces to, which we'll look at. So what I ended up doing is making that a separate component. So I made a little component called pin post. And that is a little cylindrical kind of peg that is press fitted through the press fitted through the ball bearing. And that gives us a little bit of a hole here that we can add a screw and actually affix and secure this piece to the servo arm. So by doing that, we avoid using support material and it makes it even more modular, which is great. I didn't even have to really use joints because like the main motion is all done here. I didn't have to really add another joint there because I don't really need to simulate the ball bearing in motion. It just doesn't need to. It'd be a little bit overkill. You don't really need to do that. So you can see here I have a little bit of clearances, and as I step through, I start fine tuning and extruding just a little bit out here. I actually added a hex nut, a hole for a hex nut here. So this will be kind of a cap nut. So you fit the cap nut in there, and then you can add a screw down here. And then you can basically, that cap nut will secure to the thread of the screw and then affix basically the center of the ball bearing to your servo arm so that your servo arm is free to move and all that weight is all the load of our wing will be now on that ball bearing, and it can hold plenty of weight, a couple pounds actually. So that's really the kind of the main hardest part of this, was to get all of these joints working together and figuring out how do I make this support free 3D printing, FDM 3D printing, and still modular so that I can adjust things. I think the rest of let's see what else we got here. Yeah, so I add even some more secured parts. So although we have security here, we have these two mounting holes, I wanted to mount the entire body of the servo to the holder. So I added these two tabs, and they extrude slightly inwards so that it actually clips. These two extruded walls can actually flex slightly so that it can, because you imagine this being flexed open, and then the servo gets pressed in, and then it clips back in there, and it has that extra bit of security. And then I actually even have mounting holes here, so I have a long M3 screw going out here, then through the other side, and then I can add a lock nut to secure this. This thing ain't going nowhere. It's like super secured now. So that's great. You want that because you're going to have lots of load. Looking at it in this orientation, you're going to have lots of load, and I don't want the thing to just fall out. I can't quite simulate that because I have the joints all tied there and the thing's grounded, so I can't actually move it. But you get the idea. All right, I think the next stuff is like, okay, so here we're creating the attachment for the wings, which I dubbed the wing clip. So this clips the wing to our servo arm. So this is, I foresee this being updated because we're still working out the construction of the wing. The wing itself is going to be constructed out of Bristol board using a vinyl cutter, and we're gonna heat transfer multiple materials to create this really lovely wing that has like this iridescent, transparent goodness. And we can't 3D print that. We're gonna use, like I said, a vinyl cutter to create this fairly large wing. And this guy here, these two walls here, allow the wing to go in the middle. And it's very thin right now. It's pretty paper thin, but we have plenty of surface area here to expand that out and even add more mounting holes if we want to kind of do some sort of shoelace threading where it goes in and out and weaves in and out, maybe with some wire, with some string, paracord. But right now I actually just have screws, which works well too. All right, I think the rest of the assembly is like creating another version of it. I mean, creating another servo arm. I just mirror basically that. I didn't mirror the servo arm because I just needed to mirror the servo and the servo holder so I can make sure that I can see what the distance between the two wings are going to be. And then after that, I kind of start working on the PCB holder. The PCB in this is the FeatherWing Doubler and the FeatherWing, the Servo FeatherWing. This is actually the motor FeatherWing because I was I got confused. I thought this is for stepper motors, not a servo. They're completely different. But it doesn't matter because it's the PCB is still the same size. The mounting holes are the exact same, and there isn't anything that's enclosing the PCBs just yet, so I don't have to worry about clearances, height clearances. And you can see here I have a little built-in slide switch, and this will get secured here to the backpack base plate with some more screws. And then I add the battery, and I thought the battery would work in the center here pretty well, and I still got to design like a little clip that will allow this to slot into instead of just like sticking it to the surface. And now that we've kind of gone through the end of the timeline, you can see I've added tons of cutouts to the base plate. And what is that about? Really, it's just two goals here is to just reduce the printing time. If I were to print this base plate without these cutouts, let's zoom back a little bit. If I were to print it like this, that would take maybe 4, maybe 6 hours. But with all these reliefs, all these cuts, I reduced it to just 2 hours. So this took 2 hours to print, and it's just another sketch on top, and then I just kind of assign. I'm trying to keep a consistent amount of thickness between those cutouts, so you can see here that there is some consistency going on here. And I even made some tabs for the PCB mount, and there's lots of open area here, so it's a nice lightweight plate that's still sturdy enough to house all these components without too much flexibility. So that's the kind of the strategy behind that is to just create some holes where there isn't any create some holes where it's okay to but still have a nice amount of thickness between all their mounting holes so that things have rigidity. But that's really it. At this point, we can mount this to a hat. You know, you want to do some ears or you want to do a tail or something like that. I figure I'd instead of just using, because I know it's just 2 servos, and you can totally power 2 servos off the Adafruit Feather M4, but with the 8 channels in the Servo FeatherWing, you can add ears, you can add up to 8 servos. So that's really nice, and I think that's a great way to kind of have this future-proof. So if folks want to add more things to their backpack or to their costume or to whatever it is they're making, you have up to 8 channels, up to 8 servos you can do it. So that's really cool. All powered here. All powered off of this one battery because I'm using the 5-volt mini boost because the Servo FeatherWing requires external power, but the mini boost allows you to get 5-volt, a clean 5 volts, 1 amp out of it, which is really nice. I totally recommend it. And I have links to all the products too, of course. Here's the 8-channel ServoWing. It's only $10, and it runs Arduino and CircuitPython, but I'm running CircuitPython. It's super duper easy to write sketches for it. And then this is the Mini Boost 5 volt, 1 amp. Just a little chip here that you can use a 3.7 volt LiPo battery like this one here, and when you wire up your microcontroller's V out pin or BAT pin to the VIN and ground, then you can get a clean 5 volt 1 amp out of this one pin, which is really powerful because now I don't need 2 power supplies. I just have this one battery and it's running the controller and the 2 servos without any problems. So that's awesome. Also, the FeatherWing Doubler is really great if you want to lay out, if you don't want to keep stacking feathers, you can spread them out. And for this one, I think it worked really well. You can use low profile headers, regular headers. You can solder directly to them if you'd like. If you don't want any clearance in between them, you can get it really thin. So that's cool. I'm going to have all these links in the description of the video, so check them out. Really appreciate folks ordering stuff from Adafruit. It keeps us going, and it's the best way to support the whole team, the whole company. This design will be a learn guide, or this project will be a full documented learn guide. We'll have a little video as well to go explaining an overview of the project. But I thought I'd go through and just walk through some of the CAD stuff. Hopefully folks learned a little bit of things or two, just more high level of like, what is the reason these shapes look like that, right? So if you guys have any questions on it, feel free to ask them in the comments, and maybe I'll cover them in the next video. Thank you guys so much for watching. Remember to stay safe out there, and don't forget to, well, make a great day. Bye, folks.